Okay, so the main goal of this course is to sort of reproduce this action potential numerically. And so why is that a goal of this course? Well, it's a goal of this course because that means that we have a mathematical model or sets of equations, as it were, or will be, that mimic what we see in an experiment. So the classic picture is this. So are you guys seeing a picture with a little black graph and stuff? So the picture right here on the left is the actual picture of what we see through experiment. And what we're trying to figure out is, can we determine a function whose graph looks like this? That's our goal. And so if we draw the goal, let's put this in, and we got to make sure we all understand where we're at. So if I sort of draw my XY axis, and I'm not going to draw it the normal way. I'm going to put it like this because we know the scale we're on. What we're attempting to recreate is we're attempting to recreate this picture where, let's say we're here at -70. And we know that this thing so we're trying to get this picture. I mean, this is a pretty suspect sketch, but that's what we're trying to get. And what we've got with our simple model is something remotely close, but not accurate enough. So let's make that clear. So, you know, with our first model, so you can see, I think it was homework 2. Is that the one? Yeah. Let me double check before I misspeak. Bear with me 1 second. La 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 la. Yeah, so it would have been homework 2. That's the one. So our original model, this guy, so we get the following picture. So if we take sort of our axes again, so we're getting something that looks like this. Like the shark fin is what I was calling it. And remember, this is your voltage here, and this is time. And we had something like -68 millivolts. Now, if you remember when we were doing this particular problem, I said if you read a little bit about it, what we understand is that you have a cell, and it has walls, it has a boundary, and what's happening is there's an electric charge difference between inside and outside, and there's also what we find through experiments is there's chemicals moving around, and we have potassium and chloride, and what we find out is we need to incorporate all of those, not just one into them. So if we want to get a more accurate model, we need to study not just chloride and voltage, but we need to study, like, okay, the sodium, we need to study potassium and the chloride. And so if you do that and you use some, what we say, properties from physics, and you do some derivations, what you can arrive at, and that's what the paper I gave you is all about, you can arrive at a more useful model. Now, there's lots that we have to say. So if we use some ideas from biology, physics, etc., chemistry, blah, 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 we can derive a more sophisticated and accurate. So I'm going to put the word accurate in quotations, because remember, this is just a model. It doesn't explain exactly, but it's more accurate. So this model is called the Hodgkin-Huxley equation. Named after two gentlemen who actually were awarded the Nobel Prize for this. So if you Google it, you can read all about it. So notice that this is not called the Hodgkin-Huxley equation. It's called the Hodgkin-Huxley equations. So, Zayshin, you will have taken differential equations, I believe. You took that class. And so you should have studied what we mean by a system of equations. Abdullah, you did not take that class yet, but you have seen a system of algebraic equations, no doubt. You studied those in a high school algebra course, and you've probably seen them in other places. What the Hodgkin-Huxley equations are is they are a system of differential equations. Turns out there's 4 of them. So we're going to write them down right now. So from this point on, we're just going to refer to them as the HH. So this is a system of 4 differential equations. And this might not mean anything to you, but you can translate this as they are nonlinear. And so what does that mean in English? That means they're really difficult and impossible. I shouldn't say difficult. They're impossible to solve by hand. You can study them by hand using all kinds of tools you learn in calculus and in courses beyond, but you can't technically solve them by hand. Okay, so we can't solve them by hand, but we can solve them using a computer, at least approximate their solutions. Okay, so what do they look like? Well, let's check them out because they're scary. So there's 4 equations, and they're quite ugly. So we're going to write it in shorthand first, and then we'll kind of show you what we mean by everything. Does anybody have a question yet? Maybe not, I don't know. Okay, so here we go. All right. So the first equation is going to look familiar. We're going to write it like this. C sub m, you might remember what that is, and then it's dV dt, the change in voltage. And it's equal to some number, which we're going to denote G bar NA. So this subscript of NA, this has something to do with, so if you had chemistry before, you might remember that Na is, if you find it on your periodic table, it has to do with sodium. And then we're going to write M cubed times H. And then H, this is a function. So what are we inputting into it? We're inputting into it V so this is a scary creature, as you can imagine. And we're not done. So, but before we go any further, let's make something clear. Since we're not technically deriving them in this class, what you need to understand is you don't recognize what most of these symbols mean yet. You're going to have to wait till we write the whole thing down. All right, so the next equation, that's the first one. The next equation is dN dt. So now what you'll notice is this n in the first equation, this is not just some constant. That's actually a function raised to the fourth power.
In the first equation, is it negative G at the beginning?
That's correct, yes. Now, if you Google this, you might see someone writing them slightly different, but they might write it with everything on one side, so it's positive. Okay, now, what is this equal to? Well, now there's some complicated expression in terms of V that we are going to write this down. So we're going to call this, now we have some new function, alpha of n, and this is a function of V. So we're going to tell you what all this means in a second. And then that's times 1 minus n minus some other function of V, which we're going to call beta sub n now. And then this is times n. Then you have a dm dt, and it's some expression times 1 minus m minus some other expression that we're going to denote beta m of V. And then lastly, you have an expression for H. Oops. than H. So before we go anywhere, these alpha n, this beta n, alpha m, etc., these are all functions. So we have to tell you what they are. And before we tell you what they are, let's also remember that if you take your time to slowly think about what's happening here, if you think about, okay, what's N mean? What does M mean? What is H? What do these letters represent? What do these derivatives represent? Because remember, we're studying change, right? We're asking ourselves what happens to one thing as time progresses. The top equation we're sort of familiar with. We're asking what happens to the voltage difference between inside and outside of the cell. All right, does anybody have any other questions right now before we proceed? So where do these equations come from? They come from lots and lots of experiments, and they come from ingenious ideas of comparing experiment with theory. So again, perhaps maybe I can find some more reading that might be worthwhile for you to see exactly where they come from. All right, so what we need to note now are the following. So maybe I'll annotate this to be very clear. So I'll put over here. V, N, M, and H are unknown functions. And all four of them are functions of time. So when you look at the first equation, when we say m cubed, that means this unknown m is raised to the third power. When we have h here, so the thing to pay attention to is that you'll notice all these equations depend on each other. V shows up in all four. And so you can't just solve one and then plug it back into the other. That's not how it works, because they're all dependent on each other in some sort of way, if not multiple ways. Now, Does anybody have a question or a comment? So to solve this system, to solve this, would be, your job would be to find solutions. You would need 4 functions, v, n, m, and h. So the first thing you might ask is, well, if we're only interested in voltage, why do we care about the other 3? If we only want to make that picture, if we want to mimic that picture, why do we need the other 3? Well, that's kind of the point of what we did originally. If we don't consider the actions of these other chemicals, the potassium, the sodium, and the chloride, then we don't get the full picture of what happens to the voltage, because they all depend on each other. So if we ignore some of them, well, then we're not getting a clearer picture. We're not getting the correct picture. Okay, so before we go anywhere with anything, we have to make a very important thing. Remember, our goal is to solve this thing numerically on a computer using something like Euler's method. So let's be very clear. Before we even tell you what alpha n of v, beta sub n of v, etc. mean, let's talk about how we might even solve on a computer. Now, we're not going to just start with this one because our heads will explode. We need to start with a much simpler type of situation. So when you're in algebra class, the first system you studied was an equation of 2 unknowns, or excuse me, 2 equations in 2 unknowns. So let's do that. Let's start with the most simple situation. All right. So let's think about 2 equations and 2 unknowns. So let's write a very basic one that perhaps you can even guess the answer just looking at it. So now I'm going to say, here are my 2 unknowns. S of t, excuse me, x of t and y of t. So let's assume that x prime equals y, and y prime equals negative x. So I have two unknown functions. The derivative of 1 equals y, and then the derivative of y equals negative x. So if you wanted, you could, you know, there's a lot of ways we can think about this, but this system of equations is really, if you wanted, you can write it as just one equation. Because if I differentiate the top, I get x double prime must equal y prime. But what's y prime? Y prime is negative x. So this is equivalent to me asking you what function x second derivative is minus itself. So take a moment to think about what I just did. If you're confused, please ask a question. And so with that sort of observation in mind, we can sort of guess the answer here. Notice that x of t equals the sine of t is a solution. So is x of t, you know, let me rephrase it so I'll be more clear. So notice that x of t, let me be much more clear with this. So remember, we're initially solving a solution, so, or a system. So notice x of t equals sine of t, comma, y of t equals cosine of t is a solution. So does anybody have a question about that? This is a very simple system of equations that we are able to solve by inspection. In general, that's not going to be the case. So one of the things that is it's going to be difficult is we now, if we want to learn how to solve this, we have to figure out what kind of language we should write it in so that we can sort of adapt what we already know. Does anybody have a question? This is, at this point in your life, you're probably like, what is happening? This is so difficult. It's actually not terribly difficult, but it isn't easy. I'll let you ponder this before your heads explode. Uh-oh. Are you guys seeing anything right now? Right, no, I'm trying to get Octave up for you. And I'm freezing out here. Oh, there it is. Can you guys see Octave? Maybe, probably not. No, okay, maybe you will see it Now you're going to see a picture. You see a picture now?
Yep.
You see membrane potential, and do you see this blue thing that we wanted to get?
Yeah.
So I got this using the following code, which I will share with you eventually. If I look at this scary code here, what I did is I solved the Hodgkin-Huxley equation. Okay, so anyhow, back to the whiteboard. So in general, systems are not this easy. So a couple options you might have, though, is we can use a computer. So one of the things that you might have learned about in an ODE class, it depends on who teach it, is some of the is to take advantage of, you could use an Euler method if you'd like, but there's also some sophisticated methods that are built into Octave. So let's
Can you go back for a second?
I'm sorry, what's that again?
Can you go back for a
Oh,
second?
yeah, I'm sorry.
Just writing something down.
Yeah.
Okay, I'm good.
Good.
Yep.
Okay, so one option is to use an Euler scheme. So this would be very similar to what we did before, only now we have two equations instead of one equation. So the question would be, how do you adapt it properly? So in order to do that, you have to think about, can you write it in, a language that is useful? And so we'll do that in a second. But before we do that, I think it's worth pointing out that you're going to have to be, it might take a moment or two for you to sort of to adapt to the notation. So if you get stuck, it's okay. If you're confused, it's okay. You sort of have to think about it in that manner, that some of this, oftentimes to read a couple lines to fully understand it takes much more time than you would hope. So to see how this works, I shouldn't say you're not going to do it. So let's imagine what does a 2x2 system look like? In general, it might be, our derivative x prime of t And then we have another function that's unknown, which we'll call y prime of t. And what is this equal to? Well, it's possible on the right-hand side that you just have some expression of x, y, and t, right? That's what's showing up on the right-hand side here. Some expression that is possible in terms of x, it's possibly in terms of y, and it's possible that t shows up over here, either explicitly or implicitly. And similarly, the function y that's unknown might look something like this. So again, I'm not studying the specific equation from the previous example. What I'm doing is I'm saying, how can I do this in general? Okay, now what we remember is we can write both of these out. We think about what we learned from our Euler before. So if we do this before, so if we apply it to both pieces, what do we have? Well, remember, what are we after? We're after these approximate values. So our one unknown is y. Our other unknown is x. So let's look at the first one. We have our nth plus 1 approximation is equal to our nth approximation plus our step size h times the function in this case. Now, here we have to incorporate that we might have x sub n, we might have the nth y, and then, of course, t sub n. Hi, Ricky. Hold on one second, guys. I have a visitor. Who's on? Okay, so if we apply that to the x and then also the y, then we get the similar expression for. So this is g, excuse me. So this is g, and then of course this is going to be x sub n, y sub n, comma t sub n. So I've applied Euler to both situation. And don't forget, what does your t sub n satisfy? T sub n plus 1 is just t sub n plus your step size. Does anybody have a question? Comment? Now, of course, we can't even start this thing off unless we have initial conditions, but we can easily modify that at any given time. Does anybody have a question right now? A comment, something you want to say, anything, comments, concerns? Now, we could by hand do it for the simple example before, but maybe we want to have Octave do it for us. And in fact, I'm going to ask you to do that on one of the homeworks. So We good so far before we move on? Okay, so let's see if we can knock this out of the park. I lost my whiteboard. For the problem that we were doing. Okay, so, and by the way, all right, so what I'm going to do is let's do it. So I'm going to pull up Octave. Let's see if I can. So are we seeing Octave right now, everybody? Okay.
Yeah.
Okay, great. So what I'm going to do is I'm going to start a new file. And I'm going to give it a name. So let's call it Euler. Bye, Ricky. Have a good day. So let's just call it, since we don't even know if it's going to work yet. So that I'm teaching you the ways here. This is how I call things before I know they're going to work. And then once I figure them all out, I give them better names. I'm going to call it Euler System Test. Okay. And so what I'm going to do is, and it might help if you think about the Euler that I gave you. Did I give you guys an Euler one before? Did I pass this on to you? I don't remember if I did or didn't. Nonetheless, we'll just pretend that we didn't right now. We'll give this, and we'll upload this one so you can use it. So what's the purpose of this? The purpose of this thing, what's today's date? 7, 9, 8. I keep getting the date wrong. So the purpose of this file is to solve the system. So I'm gonna say X, what was it? X prime equals Y, and then the next line was, and then the next one, what was it? Y prime equals negative X. Is that the one we started with? Yes. And so, all right, so now what I want to do is I also want to say if we need to give it initial conditions. So we think the answer is, one of the answers is sine, but what would the sine solution satisfy? Well, that would need to be x of 0 equals 0. And what is y of 0 supposed to be? Well, y of 0 would have to be 1, because so we think that these are the solutions. So again, what am I saying here? Don't forget, if we want to solve a system numerically, we need an initial condition. We have to have a starting point. And so I solved it. I think I solved it in my head or by a little bit of reasoning. And I think that x equals sine is a solution, because if I differentiate sine, I get cosine. And if I differentiate it again, I get negative the sine. So I think it's a solution. And then y of 0 equals 1. We think that's a solution, or we think that's going to be the answer. We think. Now here's the problem. Perhaps I should rephrase it differently. So perhaps instead of giving it 2 initial conditions, perhaps I give 1 condition on the derivative. So what should x prime be? Well, the x prime is the cosine, and what is the cosine? we know that that should be at 0 is 1. Any questions about this so far? All right, so if I want to do this correctly, let's be real careful. How did we do it before? We needed to, the next first thing we'll do is we'll set our step size. I'll use H. So let's say 0.01. And then what we'll do is we'll set initial conditions. What are my initial conditions? Well, my first one, now remember this is kind of scary, my very first x, which I can't do x of 0, my very first x has to be equal to 0. Oops. And then my y of 1, the very first guy y has to be equal to 1. So what are these corresponding to? This corresponds to x of 0 equals 0, and this guy corresponds to y of 0 equals 1. So let's maybe put a space here.
Wait, can you explain that again? Why is x of 1 equals to 0?
Why is it?
Yeah, I'm just not understanding why.
So are you talking about why I'm doing that?
Yeah.
Okay, so why I'm doing that is when I solved it by hand, or at least I think I did. Remember, when we solve a differential equation, all we're getting is we're getting a general solution, right? And that means if an equation has one solution, it can have infinitely many. And so since I know sine is 1, I want to get the one that is sine. And mostly because I want to test to see if my Euler works. Because if I graph my solutions, I should get a sine and cosine curve. Would you not agree? But there's other functions that satisfy this. I mean, the 0 function satisfies this, doesn't it? If you take the function x of t equals 0 and differentiate it twice, what do you get? You get 0, right?
Yeah.
So that's a solution here too, but I don't want that one. I'm looking for one, and so I'm sort of using hindsight as 20/20. If this were an actual physical problem, you would be getting these initial conditions from the problem. Think about the neuron thing we were doing, where we had the initial condition that the first time the initial was -68. So sometimes we get these numbers from actual data. Other times we get them just because we're just making them up so we can see what happens. So you can think of this as me knowing ahead of time what the solutions are. So I'm choosing these initial conditions so that I get the solution I'm looking for. Does that make sense?
Yeah, I think so.
Yeah. Right. I mean, I could choose anything I want here. I can choose anything for x sub 0 and y sub 0, but I'm going to get a different solution. Now, it's going to be in terms of sines and cosines and stuff, but it's going to be different. And by the way, part of this, had you have taken a differential equation class, you might have learned some things about uniqueness of solutions and systems. So there's a lot of stuff that maybe because you guys haven't had enough classes yet that you kind of have to learn on the fly, which is okay. But I need to be more cognizant of what you guys know and don't know when I'm doing this. Okay. Sweet. Okay, so now what we need to do, once we have our initial values, now we need to, oh, and by the way, let's suppress our, we don't want it to spit all this out. So now we need to do is we need to compute all the approximations. So what am I going to do? Well, I need to know, I need my values. I need my t's and my y's and my x's. So remember, the thing we like to do is we like to store these values in a vector. So I want to store like t1, t2, t3 in a vector I'm going to call t. And then I'm going to store x of 1, x of 2, x of 3 in a vector I'm going to call x, etc. So to do this quickly, I can use a for loop. So I'm going to say for k equals 1 to, I don't know, let's say 100 for now. We can come back and adjust if we want. So what is t of k? Well, we have a formula for t of k. T of k, well, let's be even more careful. T of k plus 1. So let's start this at 0. We'll be more. So when k is 0, I'm computing t of 1. Well, what's our initial time? Our initial time, we could put this in here, is t of 1 equals 0. Let's start at 0. We could start anywhere, but let's start at 0. So let's say, let's make sure we understand what this means. This means that the initial time, t of 0 equals 0. So what's the next time we're going to approximate out? We're going to approximate it the previous, which is t of k. So that'll be hold on, I have to adjust this or I'm going to mess something up. I should start this at 1. And then the next one is t of k, and then it's plus h. And then how do I do my x's? Well, what is x evaluated at k plus 1? Well, we know by our Euler scheme that it's, if you go back to the whiteboard, what is our x's? What's the previous one plus h times whatever my function is here. So it's the previous x, which is x of k, plus, now what is my function? My function is just y. So all this is y of k. But of course I have to multiply it by h, so it's h times that. And then my y of k plus 1 is y of its previous value, which is y of k, plus h times, now what was the function here? It's negative, so I have to be very careful or I'll put a minus. It's minus x of k. And so that is how I'm going to compute all these guys. So you might want to compare this to what I had written on the whiteboard. So what it's going to do now is it's going to compute all those values. And what we'd like to do is we'd like to see what it looks like. So what we can do is let's see, first off, will this work? If we plot t comma x, what's going to happen? So I don't want to do any modifications or anything yet. I just want to see if it works. So first thing I have to do, as you guys know, I have to name this thing, which I did, but then I have to save it. And then I have to make sure it's saved in the correct folder. And then I have to make sure the folder's here, which it is. So what I'm going to do is I'm going to give it a test run. This may work. It may not work. It may work, but it may give me the wrong answer. I might have done something wrong. This is part of the learning process. So I hit enter. And I'm going to go to my command window, and it's running. So I don't know how much longer it's going to take. Is it running? Is it running? Why is it taking so long? Did I delete it? Ah, there it is. I got my picture. So look at this picture. Does this look like we're right or wrong? I don't know. It looks like it could be right because it looks like the sine function. Remember, this blue curve should be the sine function. So let's go back to our editor and let's run it longer. Instead of stopping at 100, let's run it for like 10,000. And let's go up here. Don't forget, let's do some things. Let's clear all so it doesn't get confused. And then let's add the other guy too. And then if we wanted, we can even give it, you know, we can adjust all the other stuff soon enough. So now once I run it, oh boy. So now we see something's wrong, right? These things are sines and cosines. They should not be. What we're seeing is we've done something wrong because our graph, unless maybe we let's double check something. So one way to clear anything on the figure is do CLF. That clears any stored thing on the figure, the plot, I should say. So let's go back a bit. We started at 100. Let's go to 1,000 and let's see what happens when we run. So this looks correct, doesn't it? Does this not look like the sine and cosine? Looks like sine and cosine to me. You see the blue is the sine. It starts at 0, and then at pi over 2 is at 1, and then it hits 0 at pi, which this looks correct. And then it's -1, and then back up at 2 pi, it hits 0 again, excuse me, right here. So let's run that again, and let's go out a little further and let's see what maybe was happening. We should not be getting this growth. So what that tells us is that we're doing something wrong. So I'm going to go back here and run it again. And now I get the picture I should have been getting. So something's happening, or is something happening? Did we do anything wrong? We actually haven't done anything wrong. Why does it look correct if we run it for, say, 10 seconds, as opposed to when you look at the picture here, when I do it this long, what is the issue here? Why does it look like it's wrong? What's happening? I'll give you a hint. It starts with an E and ends with an OR. Is the Euler's method exact? It's not exact. So every step, every time we compute the next guy, we have a little bit of error. So what you see this tailing off, how it's going up and it's going down. That's not that we did it wrong. It's just that all the error is compounding after so long. Each step is an approximation. Remember, Euler's method is based off of the idea of a tangent line approximation. Does anybody have a question about this? So again, it's accurate in the beginning, but after a while, it starts really getting out of control. So here we see this is right. This is the sine and cosine. This is exciting. Whew. Does anybody have a question about this?
So like, how are we sure that this is the right answer then? If you're doing a
you mean how do you show? Okay, so that's a great question. So you don't know that it's the right answer in the sense that the theory tells you if you've programmed correctly that you are you are looking at the graph of the correct answer. Does that make sense? So the problem is, as we keep moving, if I put my cursor on this blue curve, as I start moving right, there's a little bit of air, there's more air. And after a while, it's not going to be exactly the sine curve. So there's a lot of theoretical tools, Abdullah, that tell us how accurate we can be and for how long. And how do you obtain more accuracy? Well, perhaps you choose a smaller step size. So if I go back to that 10,000 and I run it now with a smaller step size, notice it still only plots it from 0 to 10 because I've shortened my step size. And so the smaller my step size, the more accurate I'm going to be close to my initial point. But if I wanted to go, for example, to 2,000 or 20,000, and you play around with this, and that's how you get a feel for it. If we go to 20,000 instead of that, you'll see that that's still pretty good. It looks fairly accurate. It looks like it's still sine and cosine. But if you really went and studied one of these points, if I zoom in on it, for example, and you put your cursor on there, you'll see that it's not exactly, it's actually lower than -1. If you look in the lower right, I'm on that line, it's -1.01, so I'm off by almost 100th. Does that make sense?
Yeah.
But I didn't get that far off almost until, between 17 and 18, so I've gone a far way. So, and this is also, sort of the idea. Think about the actual application. In the real world, not all the time, but in the real world, if you have information about your initial point, all you're really interested in. So we only gave it exact information at 0, 0. So if we only give it exact information at 0, 0, we shouldn't expect to have information beyond that, be that accurate. Now, if we need to be accurate further out, then we adjust our analysis. Maybe we pick another point and start. Does that make any sense? Again,
Yeah,
we're on a lot of levels here. So when I say, does it make any sense, please don't take that as just as simple. It's not. Do you guys have any questions? Comments, concerns? So what I'd like you to work on is trying to use this file, which I'll put up on Canvas, to try to solve a couple systems. And then what we'll do is we'll show you actually what's nice is MATLAB and Octave have a built-in solver that's a little more sophisticated than an Euler scheme. And then we'll show you how to use that guy on Monday. Do you guys have any questions or comments? Concerns? All right, well, what I'll do is I'll upload this right now, and then you guys can make it your own. You can modify it. You can think about comparing it with the other Euler thing I gave you about adapting it. So, one of the things you might want to try to do is up top is put the inline stuff for F and G, and that way you can solve lots of different equations without much work downstairs. So, for example, what I can do is Well, maybe, yeah, I'll adapt that later. But why don't you guys start with this one, then I'll adapt it and make it a little more useful for you. And then we'll show you how, you know, to use ODE 45, which is a little more sophisticated. And that's, you know, when you have more equations than just two. Questions, comments, concerns? All right, well, look, let's end it there, and then maybe you guys can play around with this. I'll post a new assignment sometime later today, and then you sneeze, I think. Excuse me, sorry. And then we'll go from there. Any comments or questions? All right, well, thank you guys very much. I will be sure to post this stuff for you. If you have any questions, speak now or forever hold your peace. You guys good?
Mhm.
All right. Thank you very much. Take care. Be
Wait,
safe.
Professor Brody,
Take care.